Hi, everyone. Nice to see you again. Okay, so everybody always talks about success stories and what is the future and things like that. But we as engineers experiment with a lot of stuff and we fail often. And this talk is about one of those experimentations that we did and it did not work out for us. And we'll be seeing like the things that we learned and how we failed. So this is how it started. One random day, one of my colleague sends a Slack message that there's this hackathon. Do you want to give it a shot? So it was about LLMs. Obviously, that got us interested. But it was also about gaming. How many of you have played, say, Counter-Strike or any other online multiplayer games? Can you see a raise of hands? Perfect. So this was about the game called Valorant. And this is what Valorant is. So Valorant is an online multiplayer game. You have a team of 5 people. You play against another team of 5 people. You have 13 rounds that you need to win that particular game. And you have about 28 agents. So agents are basically the characters in the game, not the AI agents. These characters have different abilities. Like some of them can shoot an arrow and you can see who's behind the wall. And some of them can teleport and so on, right? So how you create your team, the agents you choose and the strategies you create is what determines how effective you are at playing this game. And you have 12 different maps in the game. Each map, again, has a different vantage point, different strategies to be applied, and so on. So for you to win the game, you need to be aware of all the maps. You need to be aware of all the agents. And you need a team that you can work with together to win the game. The hackathon was about creating a chatbot where you act as the team manager. So what they told us was, we will give you the game data for the last, say, 3 years. All you need to do is go through those logs, identify who are the best players, and then create a team of 5 people. Now, this team, again, had to be strategically the best team. You also had option, like you had to create a team based on a particular region. Like if everybody were from India, you need to select all the 5 players from India. So those were some of the rules. And that chatbot also had to have a conversation. Like if you ask a question why this player was chosen, the chatbot had to give the exact data on why that particular player was chosen and what is his strategy going to be in the game. So first, we ran the script that they gave us. When we ran the script, our laptops just crashed. And we were like, we didn't know what was happening. Eventually, we saw that there's an S3 link over there. So we just put everything to S3. That's when we realized why our laptops were crashing. Totally, we had 100 GB of data, which was spread across 3 different game leagues. And there were about 7,400 games. Each of these game files were pretty large, and that's also why our VS Code did not handle it. We downloaded some of these files and started seeing what's inside that. These files range from 200 MB to 800 MB of pure JSON. And no VS Code or any other IDE, it could not just handle the memory that is required to process these files. That's when we started using Lightsail. Lightsail is an AWS service which makes it easy for you to start services. Like if you want to start a Node server or a PHP server, there's like a one-click option for you in Lightsail. You just select the instance type and you can get running. So what we did is we took a very large Lightsail instance which had 1 TB of storage, and we put everything over there. Then we realized that after uncompressing this data, it was not 100 GB, it's 800 GB of files. So what we did is when we connected to the Lightsail, we also did a remote server establishment from the VS Code. So it made it look like you're working from your laptop, but all the scripts and everything executes on the server. So then you can process large data, which the laptop definitely cannot handle. So there are different ways you can take to process this data. We had these files, but there was no information given on what is inside these files. All it said was, this is a game file. So we started digging into what is in these files. Instead of processing all these files together, we did a sampling. We just took few random samples, some of them with lower size, some of them with larger size. There are different techniques you can use for sampling. This one worked out for us. After we took these files, we started segmenting and seeing what is in these files. But these files had every single information that was there in the game. If a player is running, at what speed is he running? What was his coordinates? If they are jumping, what was their coordinate before jumping, what is it after jumping. If they're shooting somebody, how much ammunition they have left. If they're killing somebody, at what point they kill, how much damage they're giving, was it in the head, was it in the body, and who won the round, how many times they won the round, every single piece of information. It's basically like a console.log of the server itself, and that entire JSON dump was given to us to process. So because it's JSON, all we did was print the objects of the JSON, and then we started seeing what are the different types of data we get. Then we split them into different files, and then our VS Code could handle it. So these files, again, were much smaller files than the original ones. So we started seeing on what is there in these files, and then we started to collect the metrics. From the 800 GB, we started looking at what data makes sense for us to create this particular chatbot that we wanted. And that's what we did. Over this time, we also realized that volume is not equal to data. Volume is not equal to value. Even though it was 800 GB of data that we received from the server, from the hackathon, what we eventually ended up using was around 8 MB of data. Because the data was very sequential and it had a lot of repetitions. It was necessary for the game, but it was not necessary for us as a manager of the game to kind of create these metrics. What we eventually ended up doing is creating these different data sets. We had data sets particular to a player. We had data sets particular to a map, particular to which combination worked out the best, which did not. And all of these different cumulated data sets we created out of it. And then came the question of how do we use this data? It's still a large amount of data that had to be processed. So the question is, how do we make sure an AI is going to use this information and give us the best results? So that's when we started experimenting with vectors. So AWS has a knowledge base option where you can give an S3 bucket as the source, and then you just, in a few simple clicks, you can start, it will create the vector database for you. So in the data source, we created the S3 bucket, which had all the data sets that we had shortlisted. Now, with that information, we gave the next option. So chunking is one of the most important things when it comes to designing your vector databases. That determines the quality of your data and how it is perceived by the LLM. So first, we did something called as default chunking. So what happens in default chunking is the S3 file will be given directly to the LLM, and then it's just going to read the first 300 tokens out of it, create a vector record. It's basically like a row in your SQL databases. So it did this, but when we ran queries on top of it, the result made no sense at all. Or most of the times, the query itself failed. The reason is that when it does this work on its own, it started splitting up the information that we had given in a proper structure. So data from one user got overlapped with the data from the second user, and some of this data didn't even make sense at any point. So it lost all context of who's the player, what is the game, everything else. It's just some convoluted data that is stored in the records, and it is not able to recognize any metric that we are asking it to provide. So that's when we did something called as no chunking. So here what happens is you give the same S3 source, but then with no chunking, what happens is it takes each of that file that you provide and creates a record out of it, creates a vector record out of it. So all the data sets, we started splitting it based on each user or each map. So when you do that split, that vector record becomes exclusively for that player or for that map or for that character. So that way, when you query this vector, it will be able to identify the players. It will be able to identify the maps. It will be able to get all the metrics that you wanted to get to create the team. So configuring the data, again, from the knowledge base, you have a very simple way to do it. You just select the OpenSearch as your vector store, and the AWS will automatically create the vector database. It will take the files from S3, vectorize it, store it in the database, and also give you a chatbot where you can ask questions to see if your data is valid. And this is the kind of result we got. Even when we asked a very specific question, like create a team based on combat score. Now, combat score is just one of the metric that we had stored. there were 30 other metrics that had to be processed. Combat score is a really good metric to see whether the player is good, but it's not everything. It's just one of the starting points. You need to see how many kills they had. You need to see how good they were with weapons. You need to see if they survived the end of the round. So there are a lot of things that needs to be considered. But this chatbot did none of that. And even this result, even though it looks good, these are not the top 5 players. There were players who had better combat scores in each division, and it was not able to pick that up. Then we started looking into why this did not work. So the first thing, or the first reason why it did not work, is something called as context hallucination. So what was happening is, we are giving all these different types of data. For us, it's a clear JSON structure. But when you give it to a vector database, it is not going to take it as a structure. It's just going to create tokens out of it and see what it can place in which dimension. And when we do it like this, it loses context of what is damage versus what is deaths versus what is the games. So all of this information is now convoluted, and it can probably identify 1 or 2 metrics out of it, but it's not going to go through the entire thing. The next problem is numbers. Vector databases don't do good with numbers. So for example, we know that 5, 10, and 15 are multiples of 5, right? But to a vector database, it does not understand any math at all. For it, it's always about, is 5 closer to 10 in a semantic way. So any numerical value that you provide, which in your head makes sense from a math perspective, all that context is lost when you put these things in a vector database. That's the reason why none of the vector databases will do good, especially when you're dealing with a large numerical database. So the next question is, how do we let AI use all the metrics? One of the simple solutions that we had is just write one Python script. We know what metrics are there. We just make some math operations on top of it and give the result. But that would make the entire thing more human-driven. It's not the AI that's going to query the metrics. And again, when we do it ourselves, we are sticking to a certain set of metrics which we think works. But we wanted to let the AI determine what these metrics meant for the game and then build on top of that. So that's when we started experimenting with function calling, which is basically an agentic flow, right? Or using agents. So Bedrock has this thing called agents, where it's easy for you to create these agents, create the prompt, create any kind of lambdas that you require to do the processing. So here we gave the instructions to the agent. We are basically telling it what it needs to do. And this is what we asked it to do. So what we told it was, find the best characters for each map. Once you find those characters, find who are the best players for each of this map. And after that, you get a list of, say, 20 or 30 players. Now from this list, shortlist 5 players who are the best in what they do. Now after you identify these 5 players, now assign them to each of these maps, because each map also had a different character that you had to play on. Once you do all this, devise a strategy. Who's going to attack, who's going to defend, how the entire gameplay needs to work. So all of these things we fed into one single prompt, and we expected it to work. And then we did something called as action groups. So with agents, an action group is basically a lambda. So we created one lambda whose purpose is just to query an open source database. So what we did is, instead of storing everything as a vector in the vector databases, we just stored the JSON into an open search database. And we use this lambda to query that database. So this is what we did. So from the Bedrock, when we ask a question, the internal prompt is having the capability to understand it and then query the lambda. It is going to generate an open search query and send it to the lambda. The lambda receives the query, runs it on the open search, gets the result, and sends it back to Bedrock. And then Bedrock now has very limited data available to it, so it's able to process it much more cleaner than it talking to the vector database directly. And this is the kind of result we got when we tried this. So in the result, you can see it's not just querying on combat score. It's also trying to determine how aggressive the player was. It's also determining how efficient this player was with purchasing guns or purchasing armor. It's also able to tell how many times this player has done a clutch performance. Clutch is basically when all your teammates are dead and you need to carry the team throughout the rest of the round. So it took all this information and gave it out properly. And this was also working out perfectly because these 5 players are the actual top 5 players. Like if you Google them, you'll see that they're the best in what they do. But the problem is this worked once in like 20, 30 different operations. So it was not very effective. It just works, but maybe once in a while it'll work, but the rest of the times it just failed. Then we got into why this failed. So first and the most obvious thing is that we are asking the LLM to do too many things. We are asking it to find best characters, then based on that, the best players, then shortlist 5, and etc., etc. So this is just too much for it to do. At every step, it's getting a lot of data, and then it gets confused on what the actual purpose was. And sometimes we used to get result which just said that 2 players instead of 5 players. Sometimes it just went blank. It did not give us any results at all. Sometimes it used to tell like, I don't know what information you're asking in the first place. The other challenges we had with this approach is when you use an action group with an agent, there's a limitation that you can respond with only 25 KB. So the Lambda that is querying the open search cannot return a result that's more than 25 KB. If it does, the LLM execution will fail. And sometimes the queries were very complex because it's not just finding on combat score or anything. It's also doing math operations on top of it. It's trying to find the average kills to death ratio and so on and so forth, right? It's not just direct metrics. It's also doing math on top of those metrics to find the best players. The second problem we had is sometimes the LLM used to call the action group multiple times, around 20 times, and did nothing. It just went in a loop and kept calling, trying to fetch more data, more data, more data, but without it ever reaching a conclusion on what the data meant. Again, because all of these queries had to run on an OpenSearch database, it was very specific that the queries math operation actually worked. If you give a wrong field or a wrong math operation on a field, it's going to fail. That's also what we faced. Lastly, we had something called as a frozen LLM. This basically meant that when we ran the chatbot, it just got stuck. There's nothing happening in the logs. There is no trace of it calling the OpenSearch. There's no trace of it processing anything, nothing. It's just that we run the execution. In like 3 minutes, the execution times out, and we get nothing out of it. So all of this was happening 2 days before the submission. By this point, we had tried everything that we could, or everything that we thought we could. Then we started seeing, is there something else that we can do? Because at this point, we know that our prompt is a problem and not the LLM, right? So that's when we started looking at multi-stage flows. So before the agentic orchestration came into picture, we started doing it with step functions. So with step functions, what we did is we split up this one single large prompt into different smaller LLM operations, and then tied them all up with a step function. So everything that you saw previously is now handled by single LLMs, which has a very specific purpose and a much smaller context on what it needs to do. These LLMs, again, they call the action group, they call the open search, get the data, process it. And at each step, we also started recording what is happening, what kind of results we are getting. This information, again, we stored it into a DynamoDB table, and we gave that as the context to the chatbot. So when you ask a question on why this player was chosen, it knows the sequence of events or the thought process that went into choosing that particular player. And your strategy is much more effective when you do this kind of work and you give a proper context or a proper memory to it. Everything worked until it worked together. So this large orchestration that we did, it did work once in a while again. The problem is it was not able to select 5 players, or it never shortlisted them consistently. The problem is that we are splitting it too much. It works on an individual level, but the final LLM that is supposed to get all this data together and shortlist the 5 players, that never worked out. The deadline was at 2 a.m. And like I said, we just had 2 days before trying out this entire multi-agent flow thing. And we stopped at 150. And then when I was preparing for this presentation, I wanted screenshots of things failing so I can show you the actual error messages that we are getting. But the problem is that never happened. When I tried it this time, everything worked. I didn't even have to go to the multi-stage flows. The regular agentic flow itself worked perfectly. That's when we realized the biggest mistake. What happened was the difference between the prompts is that the first prompt said or gave very clear instructions on how the LLM is supposed to think. We told it, do this, 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 and this. Like a 5-step process with clear explanation on what logic it has to use to shortlist these players, what are the metrics, and everything else. But the new prompt had none of it. The new prompt just said, this is for the Valorant game, and you have an open source database which is having this particular schema. It just named the metrics. It didn't even give explanation to what those metrics were. With that, it was able to run this properly and give us the results that we were looking for. That's when we realized that the LLM is already pre-trained on what Valorant is. It's already pre-trained on the type of games that people play. It already knows that for a particular map, what agent combination works out. All of this information is already available with the LLM, and it knows what it needs to do. We didn't have to tell it to select 5 players because the LLM already knows that if it wants to create a team, it needs to have 5 players. Lastly, when the Slack message came in, we thought it's going to be a very easy work for us, but it was not. So we spent a lot of sleepless nights, and then we eventually gave up, only to realize later the small mistake that we did that kind of tumbled down into what led to the failure. That's it from my side. Thank you.
Any questions?